Hey everyone, and welcome. Today we are diving into a topic that is absolutely everywhere, machine learning. But for now, let's just forget all the scary math and the lines and lines of code, because at its core, machine learning is really just a powerful, pretty intuitive idea, one that's already shaping your world in ways you might not even realize. All right, let's jump right in.
If you think this is some kind of sci-fi future tech, think again. It's already here. It's the invisible engine that's constantly working behind the scenes. It's what's filtering your email, deciding what's junk and what's not. It's how your favorite streaming service seems to magically know what movie you'll love next. It's even helping doctors spot tiny details in medical scans that could save a life. In all these cases, the goal is the same: to learn patterns from data to make really smart predictions, all without a human having to write out every single possible rule. So, what's the big breakthrough here? What's the revolutionary idea? Well, it's a complete flip, a total paradigm shift in how we tell computers what to do.
Check this out, because this is the core difference. For decades, programming meant you, the human, had to write out explicit step-by-step instructions for every single thing the computer had to do. If this, then that. But machine learning flicks that script entirely. Now, we give the computer a ton of data, and we give it the answers. We show it thousands of examples, and we say, here's the input, here's the correct output. Now you figure out the rules that connect them. That shift from coding rules to learning rules is what makes this whole field so incredibly powerful.
Okay, that naturally leads to the big question, right? If we aren't giving them the rules anymore, how on earth do they learn? Well, it turns out they have a few different styles of learning.
You can think of it like this. There are three main flavors of machine learning. First, you've got supervised learning, which is like studying with an answer key. Then there's unsupervised learning, where the machine has to find hidden patterns all on its own, with no answer key. And finally, there's reinforcement learning, which is basically learning through trial and error, getting rewards for good moves and penalties for bad ones. For this explainer, we're going to focus on the one you'll run into most often, supervised learning. So with supervised learning, the goal is pretty straightforward. Learn how to get from an input to the right output. You feed the model thousands of pictures of cats, each one labeled cat. Its whole job is to study those examples so intensely that it can eventually look at a brand new picture it has never seen before and go, yep, that's a cat. It's almost exactly like a student cramming with flashcards the night before a big exam.
But this process of learning isn't always so simple. In fact, probably the biggest challenge in all of machine learning is something I like to call the Goldilocks problem. It's this constant struggle to find a model that isn't too simple, isn't too complex, but is just right.
And it all boils down to this one crucial question. When that model is studying all those flashcards, all that training data, how deeply should it memorize them? The answer to that question is everything. It determines whether the model will succeed or totally fail when it faces the real test. On one hand, you could have a model that's just too simple. We call this underfitting. It's like a student who barely glanced at the textbook. The model is so basic, it just completely misses the real patterns in the data. We say it has high bias, and honestly, it performs poorly on pretty much everything. Then you've got the sweet spot, the goal we're all shooting for: good generalization. This is the model that captures the true underlying pattern, the signal, while being smart enough to ignore all the random, irrelevant details, which we call the noise. This is the model that aces the final exam. But on the other extreme, a model can be too complex, and this is a really tricky problem called overfitting. Think of a student who didn't learn the concepts. They just memorized the exact answers to the practice questions. This model learns the noise and the signal. It looks perfect on the training data, but the second it sees a new, unfamiliar problem, it completely falls apart. So how do we stop our models from becoming these obsessive overachievers that just memorize everything? One of the most powerful techniques is called regularization. The way it works is by adding a penalty for being too complex. It's like giving the model a budget and saying, hey, you can't learn everything. You have to focus your resources on learning only the most important patterns. It's a fantastic way to gently push the model back towards that just right sweet spot. Okay, now that we've got the core ideas down, let's take a quick peek inside the data scientist toolbox. Because there isn't just one magic algorithm for everything. Instead, there are lots of different tools, and each one has its own special way of thinking about a problem.
First up, we have the support vector machine, or SVM. The intuition here is just so cool. Imagine you have two groups of dots on a page, like blue dots and red dots. The SVM's job is to find the single best line to separate them. And how does it do that? It finds the line that creates the biggest possible safety margin, or street, between the two groups. It's like it's trying to make that dividing line as robust as possible. Next is an awesome tool for taming complexity: principal component analysis, or PCA. Imagine you have this massive, messy cloud of data in like 100 dimensions. It's impossible to look at. What PCA does is find the best possible camera angles to view that data from. It rotates everything around to find the perspectives that show the most important structure, making it way easier to see the big picture. And then, of course, you have the heavy hitters, neural networks. The best way to think about a neural network is like a factory's assembly line. The data goes in one end, and each layer in the network is like a station on the line. It takes the work from the previous station and performs a new, more complex task. The first layers might learn to spot simple things like edges and colors. Later layers combine those to see shapes. And by the end, the final layers can recognize entire objects, like a face or a car.
But just because they're powerful doesn't mean you use them for everything. You wouldn't use a sledgehammer to hang a picture frame, right? You typically bring in a neural network when you have a massive amount of labeled data, when the patterns you're looking for are incredibly complex, or when you're working with messy stuff like images, sound, or text, things that simpler models just can't handle very well.
So, we have the core concepts and we've glanced at the tools. But how does this all come together in the real world? How do you go from a cool idea to an actual working model? Well, it's not magic. It's a really disciplined engineering process.
This is the machine learning pipeline, and it's how projects get done. You start by collecting and cleaning up your data. That's huge. Then you train your model, you test it, you tune it, and then you deploy it. But here's the key. It's not a straight line. See that last step, monitoring? That's crucial. You're constantly watching the model, and that monitoring often sends you right back to the beginning to collect new data and start the whole cycle over again. It's a loop. And that discipline is what separates theory from success.
And all of this brings us to one final and maybe the most important question. We've established that these models learn from the data we give them. But what if our data is flawed? What if it reflects our own biases, our own blind spots? You know the old saying, garbage in, garbage out? Well, here it's bias in, bias out. A model can only ever be as good or as fair as the data it learns from. And that puts an enormous responsibility on the humans building these systems. So the real question isn't just, can the machine learn? It's, what are we teaching it?